Wi-Fi has become totally ubiquitous. It's something we all use but don't really think about. When the IEEE put out the first Wi-Fi standard in 1997, it had a maximum upper speed of 2 megabits per second. The newest amendment to that standard, which is still in draft form, has a maximum transmission of 3.39 gigabits per second to one station. That's a 1,700-fold increase in the last 20 years. We talk a lot about Moore's Law and like it's 2 times transistor density every year. We've hit like 85 times over every year for the last couple of years. So it's a grab bag of magic tricks that we throw together to make this happen. So here's an overview of how Wi-Fi works. We get data in and we get estimated data out. So the first thing you do is compression. This is kind of like how gzip works. It uses Huffman codes and other things to get your bits of data down into smaller pieces. Then you run this through channel coding algorithms. This throws in redundancy and error correcting. It's kind of like thinking about uncompression, where you take your data and you repeat it 3 times over, but it's not quite. It's more like a series of complicated checksums that allows you to reconstruct the data at the end. So once you have the bits you're sending, you want to turn them into radio waves, and this process is called modulation. You take your bits and you turn them, and you like mess with the sine wave to turn it into information you can send. And then you just mess it up completely. You send it over the air, which is a totally noisy channel. There are people talking all the time, there's microwaves, which are the worst. And then you repeat the whole process in reverse. You demodulate, you decode, you decompress. So I'm going to concentrate on modulation and transmission, which is the least programming part about this, but it's where we've seen most increases happen. So let's talk about why this is hard. So there's a theorem that says, for a given degree of noise contamination, there's a maximum rate of digital data that you can send nearly error-free through the channel, because error correcting codes. So the bandwidth, the channel capacity in bits, depends on your analog bandwidth, the number of frequencies you can talk over, and your signal-to-noise ratio, which is the signal you're transmitting at compared to the background noise and everything else going on. So we've been squeezing out performance from both variables. So getting more out of bandwidth, if you have more frequencies you can talk over, if you have more space, you can encode more information in. So let's do a quick overview of modulation. You may have heard of AM or FM radio, amplitude modulation, or frequency modulation. Wi-Fi doesn't use something the method it uses isn't too different. You adjust your phase and amplitude over a number of different variables to encode different numbers of bits in. So RF engineers represent this as a constellation diagram. You can kind of see that as polar coordinates, where you can see the phase offset in this direction and the amplitude you're changing this way. So one thing we've been doing is to make that constellation denser. You can encode more information in by having different values for each of these things. So we saw a 8-piece constellation here. This is 16, and we've gone up to 256. That's a lot. That's super dense. That's 16 bits per symbol that you're sending out at a 4 nanosecond space. And it's crazy that we can actually detect those changes at such a small level. So this, again, noise. Noise is hard. And noise knocks out the symbols that you see into different places. So the separation between these symbols gives you your noise tolerance. And if you can't tell what the symbol originally was, you can't really decode it. So what happens, so we use something called link adaptation to do this. If you see that your channel's especially noisy, you can back up and make your modulation less dense, which is one of the reasons why, as you back away from your router, things get slower and slower and slower. You see more noise, so you negotiate down to a lower modulation, so you can't go as fast. So these decisions are highly dependent on your signal-to-noise ratio. So one way you can optimize bandwidth is also by having more bandwidth. So you take a 20 megahertz channel, and you can split up that 20 megahertz channel into 52 independent streams that you're talking at once. If you have a 40 megahertz stream, you can send things twice as much. The newest draft protocol uses 160 megahertz channels, so you can send things 8 times as quickly. So your transmission speeds increase almost linearly with your bandwidth because you can just split it up into more separate channels. The issue here is interference. You can think about slicing off a piece of bandwidth for yourself as like getting a table in a crowded crowded restaurant. There's a lot of stuff going on at 2.4 gigahertz. It's really hard to find a table for 16 at 2.4 gigahertz. So you can move up into the spectrum up to 5 gigahertz, where not many people use it, or like up to 60 gigahertz, which like is Wild West. There's no one up there. Partially because you can't go as far with it. Higher frequencies drop off in range really quickly. So we might be seeing faster internet, but you can't use it across like your 5-story house, which I wish I had. So we'll talk about getting more out of your signal-to-noise ratio. As we were talking before, your signal-to-noise ratio depends on how tightly you can modulate things. And also because you don't have to repeat yourself as much, you can say more. So basically, if you're speaking louder, you can speak faster. And we can't fix background noise. There is noise in the air. And our signal power is limited by the FCC at 1 watt maximum. So you can't really like keep sending more information out and like turning up your power, partially because you might mess with other people in your area, and partially just because the FCC. So we'll talk about sneaky tricks to make power higher at localized points instead of making our average power higher. So one of these things is beamforming. So you can send the same signal twice at half the power from 2 antennas and rely on the interference between these multiple transmitting points. It's kind of like throwing stones in a pond and seeing this warped checkerboard pattern go out with different power levels. So I'm going to use quantum mechanics to explain this, because you may have seen the double slit thing. It feels silly relying on that as a tool that people understand, but... So you can use this interference to double the intensity at points. So you can see here that this is the same intensity at both points in both diagrams, but there are some points where you have double the power and some points where you have no power. So you end up with about 1 watt on average. And this is directional. By changing the phase difference between the 2 antennas, you can send it out to particular points. This is kind of like how your ears hear direction, where one of the transmitters, the receiver, sends out a synchronization pulse, and the transmitter listens to this on multiple antennas and figures out where it's originally coming from, and then shoots a signal back with the same phase offset. So this requires explicit feedback, which hadn't been baked into earlier protocols. They were kind of like, yeah, people will figure out how to do feedback for beamforming, and it now exists as something that's baked in. So we might see this happening soon. And this is one of the reasons you have multiple antennas on your new routers. It's not because they look cool, but that is one thing. And I promised you some cheating of Shannon's law. Of course, like with most things in physics, it's not really cheating. You just adjust your model to account for more variables being thrown in. So this is another form you can use multiple antennas to deal with things. This is called spatial multiplexing. And what's happening here is that you send separate independent streams over separate independent antennas in physical locations. And and you hope that the channel is different enough for each transmission because of things bouncing off of places that you can resolve where the stream is coming from at the original point. So one way to kind of think about this is like the lens in your eye being able to distinguish between things at multiple places and seeing streams coming from multiple places. But this is really wild, and the math is crazy. And this only really works in some very small cases, but this is one way where you can send multiple streams out at the same frequency, using the same channel, and still be able to resolve it at the end. So this is what exists now in the protocols we have now. In the future, we might see some more crazy things. One of the most exciting things to me is multi-user MIMO, which is multi-user using many antennas. This is kind of like the beamforming we saw before, where instead of talking to one station at a time, you can talk to multiple stations by relying on beamforming to increase intensity at some points and null them out at others. So I can have conversations with 4 people at once by like directing exactly who I'm talking to and expecting it to null out elsewhere, which is insane. Like we're going from being able to use one antenna at one time to one person to utilizing the channel to talk to many, many people. The other thing I was alluding to earlier is having more bandwidth. If you go up to 60 gigahertz, which is one thing that's proposed, you can carve yourself out 2 gigahertz channels and still be totally okay. And that's a huge bandwidth increase, both in the analog